we have the problem of an individual being accelerated in a rocket sled and then brought to rest very quickly. Information being that he speeds up from 0 to 282 meters per second in 5 seconds and then is brought to rest in an interval of 1.4 seconds. We want to calculate his accelerations. Now your textbook uses the word deceleration for an acceleration that's in the direction opposite the velocity. Okay, because that's going to slow things down. If the acceleration is in the same direction as the velocity, it's going to speed things up. So it's not a bad word. I tend to want to avoid it, but since your author doesn't, I'll live with it and explain it as we go. Okay. In my preferred scheme of things, velocity can be positive or negative, acceleration can be positive or negative, and you don't need to worry about a word like deceleration. Still, there's a good argument for the concept, so I'm not dismissing it by any means. Okay, I just have a preference that's a little different than the author's. They have very good reasons, so I'm not knocking them at all. Okay, well, what do we want to do? We have initial velocity, delta S, A, delta T, VF, the quantities in terms of which we model uniformly accelerated motion. In addition, there's the V bar and delta V that we use to reason things out and to think about what's going on with uniformly accelerated motion. Well, for the acceleration phase, the initial phase, we sped up from 0 meters per second to 282 meters per second, and I'm going to use the orange color to solve that part of the problem, and I'll use the green color to solve the problem when he's then brought to rest. Okay, for the orange problem, for the speeding up part, his initial velocity is clearly 0 meters per second. Final velocity 282 meters per second. Delta T is 5 seconds. Now, the thing I want to emphasize here is I've written out these 5 quantities and I've circled the ones that I can identify. If you're having trouble solving the problems and you aren't doing this, you ought to be doing this. Okay? This is just automatic. You write down the definitions of velocity, average acceleration. You be able to write that down at any point. You do the thing that we've talked about with the triangles. You do all these things. If you're having difficulty with the problem, and you write out the equations of motion as well. And you use those things in various ways to get a grasp on what the problem is telling you and what you're able to determine in the problem. If you aren't doing those things, if you're just going by intuition and feel, if it's working for you, okay, but you need to have these procedures ready to use when your intuition breaks down. Okay. Now, having identified V naught, delta T, and VF, we understand very easily that we can find from V naught and VF the change in velocity, or if we prefer, the average velocity. What we're trying to determine is the acceleration, which is going to involve the change in velocity. So to get to the acceleration, we'll immediately combine V naught and VF to get the change in velocity. Doesn't hurt a bit to combine them and get the average velocity as well, but that's not going to help in getting the acceleration, which is rate of change of velocity with respect to clock time, which is change in velocity divided by change in clock time. So we divide the change in velocity, which we've calculated from the initial and final velocities, by the change in clock time. We get the acceleration. Very straightforward calculation. Okay. Then for the other phase of motion, we identify initial, final velocity, and time interval, all of which are given to us. In this case, we're coming to rest. Initially, he's moving at 282 meters per second, and he comes to rest at 0 meters per second, which is the final velocity, and this whole thing only takes 1.4 seconds. It's not much time to come to rest from 282 meters per second. I'll comment that 282 meters per second is probably faster than most of us have ever even flown. you get a good tailwind from west to east, you might hit 282 meters per second in a commercial jet. And that's ground speed, that's not air speed. Okay, but that would be very fast for a commercial jet. So for what the author wants to call the deceleration phase of the motion, the change in velocity is final velocity minus initial velocity, which comes out to negative 282 meters per second. The acceleration is then, again, reason it out, average rate of change of velocity with respect to clock times change of velocity divided by change of clock time, delta V over delta T. This isn't the definition. The rate of change, the words are the definition. This is what we get from the definition. Anyhow, delta V is negative 282 meters per second divided by 1.24 seconds gives us approximately 200 meters per second squared. Now, it was requested that you express this in G's. So let me go off screen for a second and write a couple of things down, and we'll see how we get G's. A G is the acceleration of gravity. So 1 G is 9.8 meters per second squared. Now, we often round that off to 10 meters per second squared when we're doing quick and approximate calculations. And that's legitimate in this course, as long as it isn't specified otherwise. So anyhow, if you haven't already figured it out, think about how many G's that would be. I'm going to write it out. Okay, 1 G is the acceleration of gravity, 9.8 meters per second squared, which is approximately 10 meters per second squared. So 200 meters per second squared. Now we got negative 200 meters per second squared here, but when we're calculating G's, we don't worry about plus or minus. 200 meters per second squared then is about 20 G's. Okay, because if 10 meters per second squared is 1 G, 200 meters per second squared will be 20 of those. 20 times 10 meters per second squared is 200 meters per second squared. So we get about 20 G's. And you can always just divide an acceleration by the acceleration of gravity to figure out how many G's you're talking about. I'll also mention that 20 G's is not an extraordinary acceleration. You can walk away from a 20 G acceleration pretty much uninjured. You might have some bruises depending on what it was that caused the acceleration. It's not a physically dangerous acceleration to a healthy individual, provided it doesn't last very long. If it lasts a little while, I mean, you pass out at 10 G's after a few seconds. You pass out long enough, you starve your brain of oxygen, you die. If you sustain the acceleration that caused you to pass out that long, you're going to starve your brain of oxygen and become impaired or die, depending how long it lasts. 20 G's, you don't want it to last very long, obviously. But in a short collision in 1.4 seconds, it's not going to do you a lot of harm. I forget what the limit is, like in an automobile collision. A 20 G acceleration is not at all unusual as long as you're restrained and don't get injured by crumpling metal and so forth. You'll probably survive. You'll almost certainly survive without serious injury if nothing else hurt you. You get up to 50 G's, and I think maybe that tends to be fatal, somewhere between 20 and 50. I don't remember the numbers. Worth thinking about. Okay.